For the last of the learning tasks on page 2, you'll be asked in number 26 to think about these sequences, each given as a list of numbers, and to classify each sequence as arithmetic, geometric, or quadratic. Based on your observations earlier on the page, you hopefully figured out what makes each type of sequence work. Arithmetic sequences are sequences that require adding or subtracting a number to generate the next number in the pattern. Geometric sequences require multiplying or dividing in order to generate the next number. And quadratic sequences involve some sort of square pattern. So once you've got that differentiation relatively clear, then you'll really be tasked with looking at a specific set of numbers and associating one of those words with the pattern that you see. So I'll do an example just so you can kind of hear the logic behind my thinking, and then you can apply this logic to the other questions. In letter A, for instance, we've got this pattern of numbers: 1, 1/10, 1 100th, 1 1,000th, and so on. We need to figure out the next number, which means we need to identify the pattern. Now, it may be difficult because these have fractions to think about a pattern that could work for an entire fraction. So sometimes with fractions, I recommend thinking about a pattern for the top and a pattern for the bottom separately. And since the 1 is kind of the odd one out, since it doesn't look like a fraction where all the other ones do, you can consider there to be a 1 in the denominator, like we always talk about with fractions, if that helps give you something to go on. Now, if I'm looking at the pattern of the top, or the numerator, I can see that it's always going to be a 1. So it seems like a fair assumption that if the pattern continues, the numerator of the next term is also going to be a 1. But let's focus on that denominator for a second. The denominator has a 1 and then a 10 and then a 100 and then 1,000 and then 10,000, and I can clearly see that each number in the pattern has another 0. If you think about that in mathematical terms, the question is, well, what's happening to each number in order to generate the one that follows? So we could say that the pattern is add another 0, and that can help us predict what's going on in the next missing term. But let's be a little bit more mathematically rigorous. Let's think about what's happening. In the denominator, to get from a 1 to a 10, I know that there are a few ways I can do this. I can add 9. That would make sense. I could multiply by 10. That would make sense. But I want a pattern that works for every single set of terms in this list. So think about adding 9, and you'll soon realize that falls apart. 1 plus 9 is 10, but 10 plus 9 is not 100. So multiplying by 10 seems to be a logical choice. 1 times 10 is 10. 10 times 10 is 100. 100 times 10 is 1,000. 1,000 times 10 is 10,000. So in terms of pattern finding, I know that multiplying by 10 is definitely the pattern generator. Now, because the numerator technically also has a pattern to it, you can consider that the numerator is multiplying by 1. Relatively insignificant. It seems pretty trivial to say that, but generating some sort of consistent pattern here is key to the fact that this is geometric. Because we are multiplying by something in order to generate each next term in the sequence, we can classify this sequence as a geometric pattern. Eventually on page 3, where we get a little bit more formal about things, we'll also identify something called the sequences multiplier. But if you want to start thinking about that vocabulary now, just so you're prepared when you get to that next task, the multiplier is the actual number that you'd be multiplying by each time you want to generate a new term. So if I think about it, 1 times 10, 10 times 10, 100 times 10, 1,000 times 10, and now 10,000 times 10 is going to generate the next number in the pattern. But I want to make sure I'm clear, the multiplier isn't actually 10. And you might be thinking, wait, of course it is, Herbert, what are you talking about? Technically, 10 is the multiplier of the denominator, but the entire sequence has a numerator as well. So we actually say that the multiplier for this sequence is 1/10, because the numerator's multiplier is 1 and the denominator's multiplier is 10. So lumping them together into one collective multiplier gives us 1/10 as the official multiplier for every set of terms. So For each of the following questions, if it is geometric, see if on the side here you can identify its multiplier, just to get into the habit of thinking in that term. That vocabulary is new to us, but will definitely be used a lot throughout this packet. If something is arithmetic, namely that it has an adding or a subtracting pattern, then it won't have a multiplier. A multiplier is named fairly obviously because it involves multiplying. If you have an arithmetic sequence, we generally refer to its pattern generating number as a common difference. But for the sake of vocabulary and symmetry, I actually like to call it an adder. So if you have an arithmetic sequence, see if you can identify its adder. And I'm using the word adder there to kind of mimic the word multiplier that we have for geometric, just so you can start thinking about that number that makes the pattern grow. 1/10 is the number I need to multiply by to make the pattern in letter A keep growing. So if letter B involves adding or subtracting a number, which you can probably tell it does, see if you can start calling that number an adder and identify it just to get that vocabulary a little bit more natural. The last task, again, is just to finish number 26 for now. But if you feel as though you have some momentum and you feel like you really do understand the difference between arithmetic and geometric, if you feel like the vocabulary is making sense, maybe you like finding patterns, then consider pushing yourself on to page 3 and find the videos in the separate playlist for page 3. That page will give you a little bit more formality and you'll start to find more problems kind of like this.